Hello, we're going to be going over physiological lung discussion things. Anyway, so we're going to talk about physio lungs. I'm not exactly sure where this is going, so it's just going to be kind of a random topic review. All right, so we talked about, you guys mentioned that you wanted to go over VQ and some definitions, and then we'll get to the Haldane and the Bohr effect and those things that are in the blood. So starting off with, here's a lung, okay? It is a beautiful, gorgeous lung. It is absolutely perfectly anatomically correct. So we have some alveoli. Let's just make that, so this is the main bronchi going down. You have some alveoli coming off, and you have a whole bunch of segments. So here are a freaking ton of alveoli inside of that bronchial segment. Then you have the middle one, and this is not what it looks like. You have a whole bunch of alveoli there, and then you have a whole bunch of alveoli down here. Okay? So, starting with, actually we'll do VQ right after we talk about the difference between anatomical dead space, alveolar dead space, and physiologic dead space. Okay? All right. Alveoli are going to have capillaries with blood going near them. Okay? And so this is going over the top, it's going behind the back, and you've got capillaries all over the place. Okay? Behind the back. All right, so you have capillaries down here too, and they go over the top and everything. So they surround all the alveoli. So the alveoli are going to have air in them, ideally. The capillaries are going to have blood. Now, when we're talking about dead space, the bronchi right here, they never have capillaries next to them. They never exchange air with blood, and therefore they never are going to increase the O2 amount in the blood. Okay? So this part, the bronchi, the trunk here, that thing's never going to increase the amount of oxygen in your blood. Even if this thing has O2 inside of it, it will never make it to the blood. That's why it's called anatomic dead space. Dead space just means not giving oxygen to the blood. Okay?
Bronchi, bronchioles.
Bronchi, bronchioles, yeah, all of that.
Oh, okay.
Primary, secondary, tertiary, all those. And I'm not sure if we've actually used the terms primary, secondary, tertiary bronchioles, but it's a thing. So, okay, we did mention it once. Anyway, any of the things that aren't alveoli are pretty much anatomical dead space. Now, next, so that's anatomical dead space we talked about. I'm using DS for dead space. I used to have one of those. All right. All right. Alveolar dead space. Okay, so I told you that there's capillaries all around these, and that's true. However, towards the top of the lungs, unless you are exercising or about to exercise and your brain is like, oh, we'd better open these up because it's doing a feed-forward mechanism, which means the brain is anticipating that you're going to need them. Or anything that makes you breathe like super deep, then you're going to have pretty close to no active capillaries. They're all going to be closed up on this top section. The bottom ones are still going to be totally open.
Why is that doing exercise?
Exercise? Because during exercise you're going to need more air, and so your body opens up the capillaries up here during exercise so that you can get more O2, more air.
So that means you won't have any alveoli dead space on the top of the lungs during exercise, or?
During exercise, all of them will be working. When you're not doing exercise, it's mostly the bottom, some of the middle down here that are doing it. So right now, I'm not using my uppermost alveoli. So if the alveoli aren't giving O2 to the blood, by definition, they are now dead space. Okay? And so these alveoli are dead space. This is alveolar dead space. So if you're exercising, then that's not dead space. But if you are not exercising and you're just chilling, then you have some alveolar dead space. Okay?
Okay. The other thing is that he's talking about like wasted air. What are those?
Wasted air?
That not mixed with blood, or how?
That's exactly what we're talking about. And so ventilation is air going in and out of things, and perfusion is blood being around there. So ventilation, if you think about air vents, what do they carry? Yeah, and so it's about the air.
Okay.
Perfusion, if you think to perfuse something or infuse something, you've made an herbal infusion, right? An herbal tea. You're putting something into it. Anyway, I'm trying to, I know that it's weird language, English stinks. So perfusion just means that it is present. To perfuse something, no, this is blood. Ventilation is air. Perfusion in this case is referring to blood. So perfuse just means that it's filled in the space around it. So if it's perfused with blood, then it would look, this is all the blood that's around it. It's perfused with blood now. Okay? So if we get rid of that, then it's not perfused with blood. So if we have ventilation and perfusion, then we can have transfer of O2 and CO2 and whatever else. All the gases. Okay? I know, it always sounds like it's that door. All right. So we have two types of dead space, and that leads us to, we get to put a plus sign right here, and we'll just make it math. All right.
So those two together can cause the physiological.
Ooh, yes, physiological. That is exactly what I was trying to spell. Logical dead space. Okay? So, yeah, and physiological dead space just means total dead space. Total functional, total non-functional dead space.
And then he said something about, on the exam, I remember exactly everything actually. You have low ventilation perfusion, and what will increase in your system is...
All right, that's when we actually go to this. Great segue. All right, so V over Q is the ventilation perfusion formula. So, really quick, V, you can just say air, amount of air. Q, amount of blood. It's actually ventilation, and then this is blood flow. But basically, it's the amount of air, the amount of blood. And so, I'm going to get rid of... no, I'm not. All right. So what you do to find out in a given issue, all right, let's say that the test question said, this person is at rest. All right, that means that the upper alveoli are going to have a lower perfusion.
Both of them will be low, right?
Huh?
Both of them will be low because, wait, hold on. You have some waste air.
So, yes, here's actually, I remember on the test, I actually wrote this out and it was super helpful. So I'm just going to forget what I was doing. I'm going to do it this way because it's actually kind of nice. Okay. So I drew 3 equations and then VQ, 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 except instead of VQ, I put, okay, well, let's say that when it's normal, you have a 4 for air and a 5 for blood flow, because your normal-ish ratio is 80%, and so 4 and 5 is 80%. All right, so that's normal. That's a normal VQ ratio, and I knew that, and that's something that's good to know, so you can reason out everything else without memorizing everything else. Okay, well, if blood flow stayed the same and air went super high, is that going to be higher or lower VQ ratio? Just do the math. It gives you a 200% or 2, whereas this one gives you a 0.8 or 80%. And so you just do the math, and then over here you can have air be super low, 2 out of 5. And then that makes so that it is, yeah, thanks, 40%. And then you can do the same thing, changing the blood. And so then you can make so that there's less perfusion with another one. And so you can have 3 4/3. And so then this would be 125. And with this...
I'm not good with math, I'm sorry.
Well, what you can see is that if air goes up, if the top number gets bigger, you're going to have a higher ventilation perfusion ratio, higher VQ. And so you can say, does this patient have a lot of air going by compared to the amount of blood, which is what this is doing. And in division, I've always found it helpful. I hated division until I figured this out sometime in college, probably 6 years after all of you figured it out. But you can read the division line as per, 10 air per 5 blood. Anyway, if that helps, go for it. So by doing this, you can figure out if someone has a low ventilation. It was asking, like, if they had less blood going to their upper capillaries, would they have a high or low ventilation perfusion ratio? Now you can say, okay, less blood, that means we should lower the blood thing. And since it's on the bottom, then it's actually going to increase your VQ ratio. So just crunch a few of them. And that's the idea of it. And if you know the original one is this, then you can figure out, okay, more air, more blood, less blood, what's that going to do to the VQ ratio? Okay? I don't remember exactly what the question said. You sounded like you were about to mention it. What was the question on the last exam? Do you remember?
Low ventilation perfusion ratio will increase what? Whatever. I don't remember.
Low ventilation perfusion ratio.
The question was asking about, in physiological dead space, what's the VQ ratio look like, I think?
Oh, okay. So if you have low physiological dead space, that means that you have a lot of, so low physiological or high?
It just says in physiological dead space.
Okay.
I think. I'm pretty sure, because
Okay.
I took notes.
So if it's talking about physiological dead space, that is when you don't have capillaries going on. So let's get rid of most of these. So that question is saying, in a place where we don't have perfusion, so it would be this guy, because we don't have blood, 1, maybe 0, we're going to have what kind of VQ ratio? You're going to have an extremely high one, because you're making the bottom number smaller. Okay? And I probably should stop writing in green, because I know that all you guys can't see that. So I guess that just makes me sadistic and enjoying your pain at the moment. All right, moving on. Does that make sense? Okay.
I think.
Well, we can keep doing it if you.
So what happens when you exercise?
When you exercise, well, you're going to want to use more of your lungs. So you're going to have blood going there.
Okay.
So just think about what would be best for you, and your body usually does that. Especially during year 1 instead of year 2. Year 2 is when we get all the diseases.
So, yes, very exercise.
I'm not sure if I asked you this one before, the iso something exercise. And
Oh,
isometric
yeah,
exercise.
isometric. So isometric is when you aren't making, so this is dynamic. This is full body dynamic. This is dynamic. This is isometric. So if you're holding a weight
You say like.
and you're using it, it's isometric. Metric means measurement or distance. And so your muscle is not getting any longer or shorter. Iso means same. So same distance, same measurement. That's why it's called isometric. Then there's concentric and eccentric, but those are just different kinds of dynamic.
I actually remember that one.
Good deal.
Not here.
All right, and we haven't talked about concentric and eccentric. We just call them both dynamic. Concentric means that you're doing it towards the origin. Eccentric means you're going away from the origin and back. Anyway. So, now, Haldane effect. Okay? After all this work, to get some... This is a blood vessel. Highly accurate. Okay? So, the Haldane effect, I'm going to make this bigger. This is Mondo blood vessel. And it is exactly what it looks like in your body. So, we have oxygen poor red blood cells, which is what all these guys are, coming in. Okay? O2 is down over here. CO2 is pretty high. The exact numbers, O2, let's see. O2 is roughly at 40. CO2 is roughly at 46. O2 will be at 95 over here. So that is a number.
In the tissue system.
In the tissues, we'll get there. But yeah, it's between 3 and 20 and 40-ish, depending on the circumstance.
In the lungs?
Huh? So this is before the lungs. And then this will be after the lungs. This is during the lungs. During the lungs, the red blood cells are going to have, they're going to pick up a whole bunch of oxygen and dump a whole bunch of CO2. Now, the Haldane effect helps that happen. So the Haldane effect, we're going to zoom in on one red blood cell here. The Haldane effect has, well, like everything, the red blood cells have some stuff sticking off them, some proteins, okay? So there is a carboxyl, COO, and there's also an amino group, and I am so tempted to write the amino, yeah, I'm gonna. The amino group is in green, because amino is supposed to be green, because I say so. That's the amino group. All right, and then we have the 4 hemes inside, which I'm going to go ahead and make red, okay? And if we actually have a blue, oh look, it's in my hand. Right now these guys don't have oxygen, so I'm going to do it like this. All right, so they don't have oxygen right now, which is why they're blue. Now, carboxyl groups sticking off to the side can pick up a proton. Amino groups can pick up CO2. And both of these help with transport of CO2 and hydrogen. By having them bound to red blood cells, it means that it's not free in the blood, and so it's not going to change the pH as much when we're talking about the acid. And then the CO2 levels, the CO2 binds better and can travel better when it's bound to the amino group. So that's one of the things that's helping. There are some other proteins that help in the blood as well. A lot of this is also in another system, but for right now we're talking about the Haldane effect, which is with red blood cells. So other proteins and bicarbonate also do some jazz with this, but we're talking about the Haldane effect. Haldane effect says when you have CO2 and a proton attached to a red blood cell, it makes it more likely that the red blood cell is going to dump off oxygen. And so that has already occurred back here. It dumped off a whole bunch of oxygen. As you created more CO2 in cellular respiration, then more CO2 bound to the red blood cells, which made it even easier to dump off oxygen. And then
Dump off oxygen where?
Back here.
To where?
Tissues, where they needed it. All the cells. You know how you use air. Okay. All right, so you've dumped it off, and now you have a whole bunch of CO2 and COOH. Well, it also works in reverse. We get a whole bunch of oxygen coming in, and every time oxygen, I should probably do oxygen in a color besides that one. All right, I'm out of colors. All right, I wish I had black. I keep wanting to reach for black, but our black is dead. Okay. O2, I'm going to make so that this lung has room to, oh thanks. So O2 comes in.
In the lungs?
Yes, it's coming from the lungs. It's coming from the lungs, and it goes down, and it binds to one of the sites. The Haldane effect is, as soon as it binds to one of the sites, it makes CO2 binding and the hydrogen binding weaker. And it's easier for those to come off now. And we want them to, because then they can come up here and get blown out. Okay? And for the CO2, and then the H will just come off and it'll be buffered. So, and it also makes it easier for another oxygen, another one, to come in, and it's even easier for the second oxygen to bind. And then it's even easier for the third and easier for the fourth. The purpose is that
the purpose is to bind the CO2 with the nitrogen, and then
there are two purposes. One purpose is as soon as you start to have a shift towards more CO2, then it makes it easier to bump all the oxygen off when you need it back here. because the more CO2 you have, the more it forces the oxygen off.
So pretty much want more oxygen, or
Where do you want the oxygen? Do you want the oxygen coming off or staying on? When you're in the tissues, you want it coming off.
Yeah.
And so the more CO2, which is coming out of the cells that are working because of cellular respiration, the electron transport chain makes CO2, you know. Well, TCA cycle. Anyway, CO2 from cellular respiration.
Okay.
And so you want the oxygen to come off. So the more CO2 you stick out there, the more O2 will want to come off. And then once you're in the lungs, it does the same thing in reverse.
Oh,
And so the more
that,
oxygen is stuck to it, the more CO2 comes off, and you want the CO2 to come off so you can get rid of it.
okay.
And then the acid is just kind of, the hydrogen is just a side thing that does the same thing as CO2. But O2 and CO2 are the two main things. If one's high, the higher it gets, the easier it is for that thing to keep binding, and it forces the other thing off, is
Makes sense.
the end of the picture. So, and that's just called the Haldane effect. Each binding makes the next binding easier and forces off the other thing more and more. That's the Haldane effect.
There's a question about that on biochem. Or well, similar.
Oh yeah?
Never mind. Maybe it was Biz. Just kidding.
Good deal. So we then have, so that's the Haldane effect. Smiley face. Okay. I don't know why, but it makes me happy. So, for anyone who wants these details, oxygen gets bumped up to 102 in the lungs, and then, it gets bumped up, yeah, it's 102 in the lungs, and then when some venous return from the lungs mingles with the blood, because you actually get a little bit of blood coming back that the lungs have used up. And
what is this coming back?
this is kind of a detail. There might be a total of one question ever on it. Basically, the lungs use blood to stay alive. Besides this blood around the alveoli, there's also just blood that's like, hey lungs, you need some oxygen, ironically. And that oxygen gets used up, and then you have deoxygenated blood, actually just a little, from some side things, coming back from the lungs, and that mixes with this too. And so in the lungs you have 102 for your 102 millimeters mercury per, atmosphere. 102 millimeters mercury pressure for oxygen. Millimeters.
Oxygen or CO2?
This is oxygen.
Oh, I thought you talked about CO2.
Talking about oxygen. So, and when the lung puts back some of its used up blood, just from that little side place where it uses it, then you end up with 95 millimeters of mercury actually in like the blood that goes out to the entire systemic circuit.
Makes sense.
And this is called a physiological shunt.
What?
Because magic. So if you want a name for this, it's a physiological shunt of O2.
What? Okay.
It's only worth a single question. So if you don't remember the name, that's okay.
I do remember that word, but how does it have to do with it?
A shunt is when you are changing the flow of something, and honestly, this is one that I haven't figured out a good way to explain. Do you have a good way to explain it?
So when you're shunting something off, you're taking a little bit of it and putting it somewhere else, and so that's what it's doing inside the lungs. It's taking some of that 102 saturation and taking it for itself, and then sending out the rest for the body. So like that little bit, the difference between the 102 and 95, that's shunted off and stays inside the lungs.
So shunt means to shift or move. So this is...
Well, that was because the lungs also need some oxygen.
Party!
Viewers at home.
So because the lung also needs some oxygen, so that's why the oxygen exchange there, and I don't know, I'm just making up story.
All right. Does it make sense even if it's a little bit like needing to be solidified?
Okay.
All right. And
So
the
the
CO2.
carbon dioxide will be high here, right? Well,
Carbon dioxide
Little.
will be low
Low.
right here. CO2 is at 40 millimeters mercury. So these are just numbers. These are things that you can just memorize. The way that I did it, if you want to know, is ballerina, 1022, like wearing a tutu. 102, I see the ballerina going in. All of a sudden, the ballerina has to get a 9 to 5 job. And so she works from 9 to 5, 95. And only the O2 right now. And then she works at that job for 40 years. And before she finally gets to do some more ballerina stuff and goes back to 102. So ballerina, 1022, and 1 is because she was an award-winning. She won an award-winning ballerina wearing a tutu. 9 to 5, works for 40 years, finally gets to do ballerina again. She probably is very old. So that's how I remembered it. You remember it however you like. And just to be complete, in the tissues, you have between 3 and 20 normally millimeters of mercury of O2. And if you go below 3, then you start having tissue death and massive pain. So don't do that. All right? So those are just numbers. Memorize them as you will. Moving on.
Oxygen?
Yeah, this is
level?
O2. For CO2, it just goes 40 to 46, and they don't really talk about inside the cells.
Okay.
So, yeah, and if I tried to say how I remember that one, it wouldn't make sense to anyone else, so I'm not even going to try. All right, moving on to the other side with the Bohr effect. All right, so we had the Haldane effect. I just think of a big Great Dane dog right here. I was looking up what a Great Dane looked like in class, and SG leaned over and was like, "That is super random. What are you doing?" Haldane, Great Dane. Oh. I still think she thinks I'm insane. That's good. I am. All right. Goodbye. Fare thee well, fare thee well. Go filthy. So.
Bohr effect, I feel like
We learned that in undergrad in physics.
for a couple of different classes, but I have no idea what is it.
It's okay. They all just sort of blur.
Yep, they do. And honestly, up until, you have to hit it several times. Anyway. Okay, so I just wanted more space for down here because the Bohr effect is happening not near the lungs. It's happening elsewhere. The Bohr effect is actually the pH buffer system. Okay, so it's with bicarbonate. And that has to do with CO2. How do we have CO2 in the blood? And there's chloride shift and junk. I don't know if I'll get that deep. But, all right, so you have CO2, which we're going to make black. You have CO2 coming into the blood.
In the system, it's circulation.
Yeah, and this is coming from cells. So there's a cell, there's a cell, there's a cell. Looks like a bad drawing of teeth. So CO2 comes into the blood. Now, there's a molecule. I'm just going to draw it like this. It is called carbonic acid. And when CO2 binds to it, then the CO2, which would be damaging if you just left it in the blood for reasons that we won't go into, the CO2 binds to it. So I'm going to stick a CO2 on the end here. Binds to it, and we call this entire molecule bicarbonate. So we had carbonic acid becoming bicarbonate because CO2 bound. So this is carbonic acid. Okay? Now, when it binds, something actually comes off, and that something is hydrogen. So, the more CO2 you have in your blood, the more acidic your blood. So, a good way to remember that, when you exhale, you're blowing off CO2. You can also just remember the phrase, blowing off acid. Because as you get rid of CO2, the acid actually recombines with the molecule. It's not the acid itself that you're blowing out, but at least for me, that's what finally got me to remember which way the acid went. So, use it if you like.
Your CO2 in your tissue bind with carbonic
acid, yeah.
together. Bicarb.
Bicarb. Yep, bicarbonate. CO2
then,
plus carbonic acid, bicarbonate.
And then when they bind together, and then you the hydrogen come out.
Yeah.
Okay.
Yep. And when you see the equation that's like CO2 plus carbonic acid goes to bicarb plus hydrogen, that's what it's talking about.
Yeah.
And there's actually one more thing over here that because it's a 3-part. And I think that it's like CO2 or something. Crumb. Do you remember?
I don't remember those two.
Yeah, I remember those two. I think that CO2 binds to something which makes it into carbonic acid, and then it goes further to bicarb, and it's like this 3-way thing. I don't remember all the details of that off my head. So we will move on, but know that there's a little bit more to it. Basically, the Bohr effect, which here's a boar with tusks. Here's his tusks. Snout.
The Bohr is the guy?
It's water and CO2.
Water and CO2 makes. Oh, and those are added to the carbonic acid, so it's water and CO2 to
Carbonic acid, yeah.
H2O plus CO2 is what makes carbonic acid
It's
itself.
CO3 and carbonic acid.
Okay, thank you. All right, and then that makes carbonic acid, and then carbonic acid will become bicarbonate. So the CO2 is actually linking with water, and then that will form the carbonic acid. And then the carbonic acid will go to bicarbonate, and bicarbonate throws off the proton. So just shift the name one thing over.
So you said something about acidosis?
Yes, and so you'll notice that we're dealing with a proton. That's the Bohr effect. The reason Bohr effect has to do with pH and is so dang important is because if you shift it towards that side of the equation, meaning you have a whole bunch of CO2 that has to be put into bicarbonate, then you're putting out a lot of protons.
Makes sense.
And so it becomes acidic. And if you don't have very much CO2, then you're taking protons and putting them back into water, and then because this can go this way too. So if you have really low CO2, then that's going to make bicarbonate turn into carbonic acid because it's going to have less CO2, and that'll make carbonic acid turn into CO2 and water. And so then this hydrogen isn't free anymore. And so this entire thing, this hydrogen, is what you care about when we're talking about pH.
Yeah.
We'll probably go into it more like later on too, once we go into like the actual diseases and stuff.
Oh yeah.
There's like respiratory acidosis, metabolic acidosis.
Lactic acidosis, ketoacidosis, which are different than, bicarbonate exactly. But actually no, those are still using, it's just different causes for high. Anyway, blah blah blah.
Yeah.
Bohr effect. Hopefully it wasn't boring. Oh, I hurt myself.
Well, what is the
Bohr effect?
A person?
Yeah, Bohr was a scientist, and he discovered this CO2 and pH relationship. You have more CO2, you're going to have more hydrogen.
Yeah, if I discover something, I will teach it very basic.
You're going to call it the thing effect. All right. The pH in the blood effect.
No, I will discover something new because it's already enough.
We don't need to know anymore.
It's already enough. It's too much already.
I'll teach you how to crochet. All right. Let's see, what else was there in the lungs? We can do the transpulmonary pressures. Woo! All right. This is one that, all right. There was a third one. There's the Haldane, the Bohr, and what's the third one? It's the one that has to do with, it's the one that has to do with pressure. We're going right there. All right.
Pressure. Yeah.
Sweet. All right. Oh, I erased my beautiful lung. Shouldn't have done that.
Should have done your beautiful one.
Not my cleanest summary. Okay. And at this point, fare thee well. All right. Lung Okay, and then around the lung we have the pleural membrane,
Membrane, yeah.
part 1, and the pleural membrane, part 2. And technically we have the root of the lung right here, and so it goes heap, heap, and credit card people calling for the 16th time trying to tell me about student debt. All right.
That was good music, actually.
Huh.
I don't know, what was it?
It was I don't know who sings it, but it's a country song.
Oh.
It talks about stuff about how to. It's someone giving advice to a younger person about how to have a good life and how to have a good relationship and all that stuff. And don't steal, don't cheat, and don't lie, and that one. Anyway.
Don't steal, don't cheat, don't lie.
Yep. And he's much more melodious because I don't sing country very often. Pleural membrane, pleural space. So we call this the pleural space. Usually this pleural membrane would be right up against, so I'm going to actually represent that a little bit better. It's like this.
Oh, that's okay.
No, this is actually going to be a little bit important. Because science.
Science.
Ooh, science. Alright, so all this is the pleural space.
First,
And then on the outside,
it's a little bit bigger than pleural membrane.
pleural space is what is inside the pleural membrane, the two sides of it. And usually they're touching each other and there isn't actually space there. But there's two membranes, and if you pulled them apart, then it would be space. And we just call that the pleural space because there's important stuff that can happen there. And so we need to call it something.
Mm-hmm.
All right, so we have ribs also that are important. And so I'm going to draw a rib, and it's coming from behind. This is behind, and then it comes out, then it comes around, and that is one rib. And I'm only going to draw one rib all the way around. The rest of them, I'm just going to draw. See how this kind of has a circle right there? Circle, 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 circle. And so we have ribs coming around, and the ribs are actually pulling out on this. All right. To be honest, what was PV equals nRT? What is the name of that?
I always called it Pivnert.
Pivnert, yeah, that's what I called it too.
Sorry.
What's the name of that stupid equation? It's something super important. As soon as everyone's
PV equal nRT.
PV equals nRT.
I
And
was going to say avocado.
avocado.
But it's not
The avocado equation. We'll go with that. All right. So this equation, which has a name, R is a constant, M stands for moles, T stands for temperature. We don't care about any of those three right now because we don't go that deep into chemistry. The two that we care about are P and V, which is pressure and volume. Okay? Now, in the pleural space right here, imagine that you had a balloon, okay? Now, if you suck on that balloon and it's already empty, it's going to like pull in on itself super hard. That is what is happening right here. And then if you closed off the neck of that balloon, it would stay sucked in on itself, right? So and then you block it off. So you have a vacuum, you block it off. That pressure is going to stay there. And that is what this membrane space is. It always is being a little bit sucked on average. And so the two walls of the pleural membrane are actually like touching each other because they're being sucked towards each other. In the lungs, you have plus or minus 1 pressure, and this is in millimeters of water. All right. And then the ribs, why is this at -5? Because the lungs are kind of pulling this layer in, okay? So it's pulling the inner membrane of the pleural membrane towards the lungs because the lungs are elastic and they want to collapse, right? And then the ribs, they're connected to your body, obviously, and so they are connected to this outside membrane and they're pulling it out. So you have one thing pulling it in, one thing pulling it out, and so that means that there's going to be this negative pressure in here because there's two things pulling on it.
Wait, what was two things? I know that the lungs.
Lungs, ribs.
Oh.
Lungs pull it one way, ribs pull it the other way. And that's why you have a negative pressure in there. Now, what happens if your ribs are forced inward? And you try and you have all the muscles pulling your ribs so that they go inward. Then that means the ribs are going to put pressure going in instead of trying to stretch it out. Now they're actually pulling it in because the muscles are forcing the ribs to go down. That makes the pressure in here go up, and it can go up as high as 30 millimeters of water pressure. And it's a high pressure, and pressure is going in, and so that means that you would be squishing the lungs. So the ribs squish the pleural membrane, which squishes the lungs, and then the lungs get smaller and you exhale. Okay?
Okay.
So, and then you stop using the muscles, the ribs expand. That pulls on the pleural space, and it goes to something like -10.
What was it about a positive 8 thing? What was
Positive 8.
He said
That's a
something-
normal exhale. So exhaling as hard as you can is positive 30. A normal exhale is roughly positive 8.
Hold on, exhale. How come it's become positive?
Positive because you have pressure pushing in.
The muscles on your ribs are squeezing it in.
Oh, is it only the muscle or not the lungs? When you get a positive pleural pressure.
Yeah, the lungs can't really change too much. They have a tiny bit of change, but pretty much all the change in the pleural space is because of muscles and ribs.
Okay.
I never thought about that before. That's good to know.
Because I was very confused about. Hold on. The lungs cannot change the number at all.
Very little, plus or minus 1. So the lungs,
Okay.
not much. Okay, now why do we care about this? Why don't we just say that the ribs pull on the lung, basically? First, because that's not true. Second, because if you get a hole in this membrane, what's going to rush in there? Yeah.
Air.
Yeah, and then this is going to fill up because it's at a negative pressure and it's like a vacuum, it's pulling everything in. And the lungs want to be small anyway, so they're going to shrivel up. And then you're going to have a pneumothorax.
So that is when the
Collapsed
pleural
lung.
pressure will become more positive.
So the pressure becomes atmospheric, and so it'll actually be at 0, but it won't be able to change anymore because it's no longer closed.
When you have pneumothorax.
Yes, and so you're at 0 millimeters of anything, H2O, and that is because all the air is in there, and you can't. If there's a hole in your balloon, no matter how hard you suck on it or blow on it, it's not going to change. Exact same thing here.
Exactly.
Okay? And the lung is always wanted to be small. And now it gets to, if there's nothing holding it out into shape. The pleural membrane is what's holding it out into the shape with that negative pressure.
What? Hold on. How's that hole then?
So with no hole, the pleural membrane is trying both to be with the ribs and to be with the lungs, right? They're both pulling on it. So the ribs are pulling hard enough that the lungs, it's kind of like a tug of war, the ribs are pulling hard enough that the lungs have to stay big.
Wait, hold on. The pleural space is also attached to the ribs or what?
Yes, it's attached to both. So when the ribs are pulling out, which they always, just because the ribs are out there.
Okay, so when you inhale then, hold on.
Inhaling makes it even more, inhaling makes the lungs even more stretched out, but
Stretched out.
just at normal, like we're just standing here, even if I wasn't breathing right now, my ribs are going to be attached, and so the lungs can't collapse because they are both attached to the pleural membrane, and the pleural membrane isn't going to move. And so if the lungs, you can think of it as the lungs almost being attached to the ribs, and they're not strong enough to pull the ribs in, and so the lungs have to stay big.
Oh, okay.
Does that make sense? Más o menos. Okay. And basically when you yes, and when you get a hole, then all of a sudden, air comes into here, and so the lungs are no longer.
So it will all shrink.
Yeah, the lungs will shrink, the pleural space will get huge, and the lungs are no longer kind of attached to the ribs.
Yeah. What? Now I remember the word inflate and deflate.
Inflate. Inflate is to put air into something and make it bigger. So inflate, or anything, it just means putting something in to make it bigger. Deflate is the opposite.
So when you have pneumothorax, then the lungs will deflate.
Yes. Yep. Lungs deflate. Pleural space inflates. And you say shoot. Because it's bad.
What?
Shoot, as in dang it.
Shoot?
Yeah, it was a joke. So.
It's like a
very
phrase.
Did I just say that word?
No, I did. I was being funny, except it didn't work.
That word is bad?
No, that's a different one. No, that word is not. There's another word that isn't good. Shoot is
That
okay.
one's okay too.
All right.
Oh man, I'm
It's just
sorry.
slang. It's okay.
Yep.
Hopefully, no one teach me bad words because I have no
I'm
idea.
gonna start teaching you bad words. I'm gonna do it.
Gasp. It's on film. All right.
Chaotic neutral.
Funnest ever. All right. Anyway, PV equals nRT. How does all this play in?
Pressure and volume.
Yep, pressure and volume. So when the ribs are putting pressure on this, then you know that the volume is basically, if pressure goes up, volume will go down. Because if you do math, make this P equals nRT over V, because you've divided the V out, then you know that P and V are going to be inversely related. If we get rid of the nRT because we just don't care, then it would look like this. P equals 1 over V, which means that they're indirectly related. All of that, if that didn't make, that's for people who like math. If you don't like math, when P goes up, V goes down. When V goes up, P goes down.
I do get that math, but I don't like it.
Okay. All right. And so if you just remember the equation, whenever they ask about it, just write the equation out and say, okay, is P going up or is V going up? Well, I know what the other one is doing. And that's literally how you
what
solve the
makes
thing.
the pressure to go up?
Lots of things could do that. In this case, I have slight asthma. I just increased the pressure by using muscles to contract and make my ribs go small. And so I increased pressure, and therefore volume started to go down. Because pressure inside here, and then inside here went up.
The volume, what volume are we talking about? The volume in the pleural space or the volume in the lung? There's no such volume.
Either. Okay? This is an equation that can work for anything, anywhere. It will just be true.
Okay.
All right?
Oh, okay.
And assuming that it is, all right, this is getting a little bit into chemistry, or physics. Assume that it is a closed system, meaning we're not adding any gas to it, any liquid to it. We're not adding anything to it. We're not taking anything away from it. So when we say increased volume, we don't mean more stuff. We just mean that the box got bigger, but it has the same amount of air.
The pressure will be lower.
Yes. Sweet. All right. And if you just remember that it's a closed system, then this equation will always give you the right answer. The only time people go kind of cross-eyed is when they're trying to add stuff to the system. And then it's like, no, it doesn't work. All right.
Okay.
Yeah. And I think that's good. Was there anything else? I can tell you a few other random facts.
Arterial pressure equal the cardiac output. That one, please.
Mean arterial pressure.
For the dynamic exercise.
All right. So, mean arterial pressure
equal cardiac output and systemic vascular resistance.
Wait.
Yeah.
Wait.
SVO.
Cardiac output.
Cardiac output.
equals mean arterial. Oh, right, I memorized it in a different order than what you're talking about, but they're both true. So I'll rearrange it here really fast.
Okay.
Systemic resistance, multiplied by systemic resistance, then you have systemic resistance times cardiac output equals mean arterial pressure. Okay. Sorry, I had to. Okay, so that's the way that you memorized it?
Oh.
Yes?
Either
No?
way.
Either way? Okay. Well, we're trying to get mean arterial pressure, so you can get systemic resistance and cardiac output. Oh, and that's for systemic. If you're talking about in the lungs,
Pulmonary.
then it's just pulmonary resistance. Yeah, so mean means average. So it's the same thing. So average arterial pressure. So you're just taking all the arterial pressures, first one, second one, third one, you just take a whole bunch of them, and then you average them. Now, and really what you're doing is, pressure goes like, so if this is, let's see, pressure would go, what is the pressure in the lungs? I knew this. Pressure in the lungs is typically lower. It's going to be something like, well, crumb cakes. I don't have that up there anymore. I'm going to have to get that back.
So if you increase your cardiac output, then you also increase mean arterial pressure.
Okay. So pressure, this is pressure. And this is time. Okay? So the highest pressure, I don't remember in the lungs, but in systemic, it's going to be basically 120. And then the diastolic pressure, the lowest one, we're just going to say 80. Okay? Now, if you took 120 plus 80 and averaged the two, those would equal 100, right? Well, we can't quite do that because, look, it's only at the high of 120 for a very short amount of time. But it's at the lower areas for longer, okay? And so really what we're doing is 80, 85, 120, 85, 80, and you take all the numbers of every single moment and average them. And most of those numbers are much lower than 120. And so we're not going to end up with 100, which is exactly in between the highest and the lowest. We're going, this reminds me of calculus. You're going to end up with something that's somewhat lower. So mean arterial pressure is the simple way to calculate it that they gave us, which is pretty good estimate, is going to be the diastolic pressure, because we know it's going to be higher than that. So we start with that, 80 plus 1/3 of the difference between these two. So 120 minus 80 is going to be 40.
So mean arterial pressure is like diastolic minus.
Wait. It's the difference between those, 1/3 the difference between those.
The difference between systolic diastolic pressure, right? Oh, that's cardiac. Oh, I don't know.
1/3 of 40, that's 4/3. That's, I'm not mathing.
I have no idea.
Anyway, that's going to give you,
94.
thank you.
93-ish.
All right, 93-ish. Great. Some days I can math for fun, other days I want to burn it. All right. So, and we see that this mean arterial pressure is less than halfway. So it's like right here, 2/3. You add 1/3 of the difference between the systolic pressure and the diastolic pressure. Does that kind of make sense? You can also just memorize the formula and not worry about y and just say diastolic plus 1/3 systolic minus diastolic, if you'd like to just memorize it. But I find that when you remember the reason, it's much easier to remember the formula. And so that's why more commonly you're at a lower blood pressure. Your systolic is only right when your heart is beating.
I remember that.
Okay. All right.
And I don't want the math either.
Sorry. I didn't know exactly what we'd be hitting today, so all right. Anything else? Type 1, type 2 cells, I guess there's a couple random bits of knowledge that we can throw out. Or we can tie up if you guys are good.
Yeah.
Tie up.
I probably want to do this.
All right. Well, good times. And just because I know that occasionally it drives me nuts, type 2, they're the ones that secrete surfactant. Type 1 are the normal lining of the lung alveoli. And if you're going to be crossing from alveoli to capillary, you're going to have to go across type 1 and capillary walls. There you go. All right. Cheers.
Cheers.